hello, good, whatever it is to whoever's there. Um, I was very happy to hear that there was a conference bringing together people from different parts of the world in probabilistic combinatorics. And I had a strange idea, and I hope you don't find it too strange. Last quarter, Stanford's on quarters, so last quarter, last year, I taught a course which was called probabilistic combinatorics. And it was in the spring quarter. Our courses are 10 weeks. It was a graduate course. I had about 40 students and several faculty, and they were students, graduate students from all over the place: statistics, mathematics, electrical engineering, operations research, computer science, and physicists. And they were really there. Our courses meet twice weekly, an hour and a half each. What I'm thinking is that some of you might benefit from the experience I had in teaching such a course and might want to teach your own version of it. In listening to this conference, I'm both impressed by the depth and breadth of the different parts of probabilistic combinatorics. And the only thing I'm afraid of is that I'll make you mad because you'll think, well, what happened to my favorite topic or my area? And well, ease up for a little while. And here's my area now. Okay, there we are. There was my course. It was taught online, and for the focus of me for the course was take some standard combinatorial object, partitions, permutations, set partitions, graphs, and pick one at random. What does it look like? And of course, that's not math, but the course will make it math. And I'm actually simply going to go through the topics I gave. It was 20 lectures, and I'll stop in the middle and I'll give part of one of the lectures so that you see what it was. And the course, well, it covered what I'll call standard topics, at least for me, but I'm sure some of them will be novel to you. One of the things I find fascinating is this Rasparov, the entrance of logic, because we all say, well, take a typical combinatorial object, and we all know what we mean. And model theory has a way of saying, what is a family of combinatorial objects? And Rasparov and his co-workers are developing things, and I'll come back to that. So here, I'm just going to actually go through the lectures, but I'll make comments and hope that this is useful and interesting, and I really do hope it doesn't make you too mad. So my introductory lecture was about metrics on permutations. And there are a lot of ways of measuring the distance between two permutations. And the most standard one, the most widely used one, is the minimum number of inversions to bring one to the other. But there are many others. And for the standard metrics, I proved, because we know they're generating functions, I proved the central limit theorem for the number of inversions and for the number of cycles in a random permutation. And I also, Don Knuth's favorite metric is the insertion deletion metric, in which you think of having a hand of cards and you take a card out from any place and put it back any place, and you want to sort the cards. And the number of operations that takes is n minus the length of the longest increasing subsequence in the pi sigma inverse in the permutation. And that allowed me to talk about the Bike-Dief-Johansen theorem. I also talked about Edgeworth corrections to try to make the results relevant for the kinds of n that are of interest, because people very often don't have permutations of length 100 million. They have a lot of permutations of length 10. so it just was to get things started. The second lecture was more detailed. The topic is cycles and permutations. So features of a permutation which are invariant under conjugation, which don't depend on irrelevant labeling, as we say. And there's this beautiful paper by Larry Shep and Stu Lloyd. And I did the pick a permutation at random. What's the length of the shortest cycle? What's the length of the longest cycle? As I'll say in a second, Poissonization and moment theory. Moment theory is a deep and classical subject, but it's disappeared from the modern curriculum. And it's not that people don't know that the normal distribution is determined by its moments, but if you look just under that, there's amazing math that was done. And in the 60s, 70s, 30s, Markov, Crane, I also talked about reality a little bit. So let me just remind you, the cycle index of the symmetric group, you sum over all permutations, and you've got n variables, and you make a monomial, which is xi to the number of I cycles, and then you add those up, and I'll divide by n factorial. That's the cycle indicator of Sn. And then if you put all the cycle indicators together, sum n equals 0 to infinity, Cnt to the n. So that's a formal power series in infinitely many variables. Polya proved early on that factors, that is, that this is equal to e to the sum of xi t to the I over I. And if you multiply both sides of this equation by 1 minus t, 1 minus t here and 1 minus t, and put it up in the exponent, so this becomes xi times t to the I minus 1. That has a probabilistic interpretation. On the left, it's flip a coin with probability of heads t of coming up heads, and until the first tail. That's what the left-hand side is, and the right-hand side is, and then you pick a permutation in that Sn, so I've randomized n, and the right-hand side is the product of the generating function of Poisson random variables. And so that says that if you randomize n, the number of I cycles become exactly independent, and so you can do anything you want with them, basically. And then, so that in particular implies that the number of I cycles are independent Poisson with probability 1 over I, and then that the length of the long cycles are given by the Poisson-Dirichlet distributions, breaking a stick into pieces that people know. And there is an issue of how you go back from the Poissonized or randomized n back to facts about ordinary old Sn. And that was the content of my next lecture. Which is, well, you do it by various methods. It depends on the analytic behavior of the right-hand side. But another topic which has disappeared from the curriculum is the topic of Tauberian theorems for asymptotics of coefficients of generating functions. If you have nice singularities, great. Then Cauchy's theorem works great. But there are very natural functionals where the singularities of the right-hand side are, there's nothing like nice. They're just defined on the real line. And then there's a beautiful, the Wiener-Tauberian theorem, et cetera. They're beautiful ways of going from the behavior of the right-hand side back to the behavior of the coefficients. Another thing I did in the second lecture was, this seems like a miracle, this factorization of the cycle index, but it's a miracle. It happens a lot. In particular, for any, instead of permutations, for any finite reflection group, the classical finite reflection groups, there's a similar factorization, but also for finite groups of Lie type. So the question becomes, look at n by n matrices, say invertible ones, look at GLN FQ, and pick such a matrix at random. and look at the Jordan blocks, or the rational canonical form of the matrix, and how is it distributed. And more or less everything similar holds. The details are a little different. And if you don't know that, there's a very beautiful paper by Jason Fullman called Random Matrix Theory over Finite Fields that develops this. Jason isn't so much an analyst or even a probabilist. He's more an algebraist, but he's good at lots and lots of things. So this picture of you can randomize a parameter and make things independent has some legs, that's all. It doesn't do everything, but it does a lot, and it's a good thing to know about. That was lecture 3. Lecture 4 might be a little unusual for this audience. I wanted to do an application of the kind of combinatorics and analysis that I've done so far to an area far outside the combinatorics and the topic. There's several choices, but the topic I picked I call measures for measures, and that's an application of cycle theory to what are called Dirichlet random measures. And everybody here knows the beta integral and the beta density, and then the Dirichlet distribution on simplex is a familiar integral. Well, statisticians work on a bigger space. Let X be any space, essentially any space. I'm suppressing measure theoretic details, and let P of X be all probability measures on X. The Dirichlet distribution is a probability on the space of all probabilities. So, and it's very simple to define, and it's very widely used in Bayesian statistics. And a kind of typical question, it's a probability statistics question, is pick a random measure on probabilities on X from the Dirichlet distribution, and then take, say, some continuous function on X or some reasonable function on X, look at the integral of X, f of X with respect to this measure. So that's a random variable because f is random. And then you can ask what its law is. And if you know Polya's theorem and cycle theory and the kinds of things we did before, there are beautiful answers to this question. And it's a nice application of the math that came before. So that was my first 4 lectures, sort of trying to do some probability and combinatorics. The next lecture is, of course, familiar, but maybe the way I did it will be a little less familiar. And I call the subject, next few lectures, I call them conditioned limit theorems. And people know them under the name of Poissonization, but and then de-randomization. But the example I gave, the Shep-Lloyd example, for example, you don't randomize n by a Poisson distribution, you randomize it by a geometric. And there's a world of when can you randomize a parameter and make the coordinates independent. And that allows you to do, and I did in some detail, limit theory for balls and boxes. So drop B balls and N boxes according to probabilities P1 up to Pn, if that's the notation I'm using, and then look at standard functionals, the size of the biggest box, the number of empty cells, the number of cells of size 1, and there's lots and lots of functionals of balls and boxes. You can do similar things for the uniform distribution on compositions, and there are similar questions for sampling without replacement. You have balls in an urn, maybe completely different, maybe 3 different colors or different proportions. You sample partially from the urn, and you have standard probability questions. Well, you can make things independent by randomizing a parameter, and then you're in the world of conditioned limit theorems. And so that was a topic which, again, I find useful. A special case, but a very important classical special case of that is, the huge topic of integer partitions of n. Um, uh, you know, pick a partition of n, I call them lambda, let xk of lambda be the number of parts of lambda of size k, and how do they go? And there are these many beautiful facts. The small parts of the partition are xk times k normalized this way has an exponential distribution, and they're all independent, at least all up to, you know, square root of n over log n or something. They're all independent. The large parts, Erdős and Lehner early on, the largest part of a partition normalized in this way has a double exponential distribution, but you can give the joint distribution of all the large parts, and they're given by a similar stick breaking argument. And what's nice is, while there are hundreds of papers about this subject, all of this stuff can be done from one point of view, and it all amounts to this factorization of the generating function for partitions. That is this familiar formula. And a mantra I said during the class, and I said it almost every lecture, is whenever you see a product, something's independent. And your job is to figure out how to say that. And if you don't know the probabilist way of doing these kinds of theorems, there's a beautiful paper by Bert Fristed, F-R-I-S-D-T, on the distribution of random partitions. And it's all done from this probabilistic point of view. There's a tiny little bit of analysis. There is a little analysis, but, and of course, it's not that probabilists can do everything, but you can do an awful lot. The next lecture was on, let me clear the decks here. Excuse me, the next lecture was on the birthday problem and coverage problems, and Aldous' beautiful theory of the Poisson clumping heuristic. So let me say that in a language which is maybe more closer to this audience. So for me, the birthday problem can be said this way. You have a graph, and that represents people who know each other, and you color the vertices of the graph by C colors, and maybe I'll pick the colors with probability P1 up to PC. They don't have to be uniformly distributed. They're independent from vertex to vertex. And then I ask the question, fix a graph, pick a coloring at random. What's the chance it's a monochromatic coloring? What's the chance it's a legitimate coloring? So that is, how many people who know each other have the same birthday? And you know, what's the chance that you have two people who know each other have the same birthday? And said that way, first of all, it's a rich problem, and I have written lots of papers on it. In particular, in case you're thinking, the graph doesn't have to be fixed. You can pick a random graph, and you can pick a random graph from very general models. It doesn't have to have anything to do with GNP. And then you can ask the same questions. And so that was the topic of lecture 7. This is a special case of what we call coverage problems. Namely, you have a set, maybe a continuous set, maybe the unit cube, and then you have a family of subsets. And what you do is plunk the family of subsets down at random and ask, what's the chance that you cover the space? How many subsets do you have to pick? And if you haven't looked at it, David Aldous wrote a book which is called the Poisson clumping heuristic, which unifies huge areas of probabilistic combinatorics in this language. And it's mostly conjectures. How he got away with it, I don't know. But I mean, he really is the great David Aldous. I mean, and so there's a lot of math to do. You know, he just says, oh, this must be true. And over the years, people have filled in things. But if it's a very, very powerful picture for unifying probabilistic combinatorics. This question of how do you go back from, if you have a generating function and you know something about the right-hand side, how do you go back and say something about the coefficients? there's a very general method which I call Lecombe's method after Lucien Lecombe, and it seems not to be known in the combinatorics community. It's not known by probabilists either, but it's known by some people, of course. And one way of saying it, which I hope will resonate to you, of course, there's technical stuff that I'm not saying, but this was my lecture 8. Suppose I have a sequence of random variables, x1 up to xn, any kind of random variables, and I have some statistic, some function of them, say a d-dimensional statistic or integers, and I want to study some other feature of x1 up to xn, conditional on tn is little tn. So that's, what happens in Poissonization. I have independent Poissons, and I condition on the sum, and then I want to know about the number of xi's that are 0 or something like that. So this setup is quite general. And Lecombe's idea is the following. He's going to say, suppose you could prove something stronger than what you need, but often that's easy to do. Suppose you could prove that the joint distribution of Tn and Un, n is going to infinity, the joint distribution of Tn and Un as n goes to infinity has a limit, Tu. You have to normalize that this has a weak limit. Then, and there are mild conditions, but they're not so bad, the conditional distribution of Un given the sufficient statistic, which is what you want, converges to the law of U given T. And often, these are bivariate normal and you know everything about them. And there are two circumstances. Sometimes the conditioning doesn't matter, and sometimes the conditioning does matter. And you can, so this is a beautiful general theorem. And there's a very nice paper by a statistician, probabilist named Lars Holst, H-O-L-S-T, which explains Lecombe's method and works out its connection to Poissonization. But we do it, for example, if you look at the maximum number of balls in boxes, if you drop n balls into n boxes and uniformly, and you look at the maximum box count, there's no limit theorem. That is, you can't subtract off an and divide by bn and get a limit. It oscillates. There's number theory in there. But this theory, it just does fine. It just doesn't, it handles it all quite well. So this little piece of lectures all fit together, and let me just say, the last lecture, lecture 9, there's this subject of randomizing a parameter, make things independent and going back and unconditioning, has a name in physics where it's called equivalence of ensembles. You want to do statistical mechanics in the language of the microcanonical ensemble. You fix the energy, and then you think the system is a random point on a constant energy surface. And that can be hard to do. And what you can do is randomize the energy. They talk about having a heat bath, and then that gets you the canonical ensemble, or maybe the grand canonical ensemble. You do your calculations there, and then you need to, if you want to, what we want to, you want to go back and argue about the microcanonical ensemble. And there's a mantra, which is that all the ensembles are equivalent. That's not true, but there's a lot of truth in it. And so this picture of equivalence of ensembles, I certainly explained and said what people like Varadon and Oscar Lanford did about that. It's very, very close to the work I do on Diffinity's theorem. And that's something that we heard about. Well, she didn't use that language, but Jane Gao, part of the wonderful talk she gave in this conference was, how do you go back between an Erdős-Rényi model and something which, say, conditions on the number of vertices, or that it's deregular? That's equivalence of ensembles. And some of her techniques and the techniques of the Australian group were new to me and interesting. But if you don't know the connection between equivalence of ensembles and Diffinity's theorem, I've written about it endlessly, that's something that I talked about for 2 hours. Okay, there's one other aspect of it, which is very, very interesting, and I think that it's an area that has a lot of research to do. I should have said that my lectures were aimed at graduate students and young researchers, and I was trying to say things there are to do. Conditioning in the corner can lead to very interesting different behavior. And so let me just give an example. Probably everybody in this audience knows that if you pick a point at random on a high dimensional sphere and you know, look at, say, the sphere of radius 1 and look at the first coordinate and multiply it by root n, that has a Gaussian distribution. And that is a special case of equivalence of ensembles for the free field, for no constraints on the energy. Just the sum of squares is fixed. And that's true, actually, if you look at the first little o of n coordinates, they're all independent Gaussians. But of course, all n coordinates, they behave differently. You know, they live on a sphere, and product Gauss measure doesn't live on a sphere. Well, what if you're in the corner? Or what if you look at the intersection of a sphere with a plane and pick a point on that intersection? That's a one-dimensional lower sphere. But Cauchy-Schwarz put some constraints. If you know you're on a plane and on a sphere, so if you're in the corner of the Cauchy-Schwarz inequality, the naive picture of equivalence of ensembles breaks down, and physicists have discovered that numerically, and you can prove various things. And that's what I mean by conditioning in the corner. Whenever you have two statistics that you're conditioning on, and you're at the corners, interesting analytic behavior occurs. So that was my ninth lecture. So just to pause for a second, the second set of lectures was about condition limit theorems and going back and forth and randomizing a parameter. And there's some theory that says when you can do that and when you can't. So, almost all, I was trying to think what's the difference between what I do and what many people in this meeting do. And I think you get a flavor for it in this first set of topics. What I find many people do, not everybody, of course, here is use probability tools to prove things about combinatorics. And I'm using combinatorial problems to prove new probability problems, to suggest new probability problems and to work on them. And that has a little bit of a different flavor. For me, a very, you know, coarse upper and lower bounds, hard as they are, and much as I have respect for them, I want a limit theorem. I want numbers. I want something that's interesting and useful when n is 100. And of course, that's hard to do in hard problems. It's hard to do in the equivalence of ensembles type problems. Physicists work with Hamiltonians that are fairly complicated, and the kind of nice factorizations that I was using don't hold. And all you can hope for is large deviations. If you have a rare event in the canonical ensemble, then it's rare in the microcanonical ensemble. But okay, I'm going to change topics now, and so this would be a good time if I can trick anybody into asking a question, please, or making a comment, or if I insulted you. Come on, Russians. Australians? Australians aren't polite.
Both. How many students did you have for this?
In this course, I had about 40 students, and several faculty came. 35 students did, in order to get a grade for the course, there were two final projects, which were 10 to 15 page papers. And I gave a list of topics. I didn't let them do whatever they wanted. Of course, if they wanted to change things, they could present it. But I gave a list of topics. They had to choose one, and then they had to submit, you know, a 3-page, here's what I'm going to do. And then in the middle of the course, there was one paper due, and at the end of the course, there was a second paper to do, and it could be that the second paper was a continuation of the first paper. I had 35 students hand in final projects, which I had to grade and make comments on, and 3 of them are published papers now. So that's the structure of it. There were a few undergraduates that came, but basically I wanted to teach graduate students probabilistic combinatorics, and you know, I assume they know probability and complex analysis, and they know math, and they're like Russian undergraduates, right?
Percy, I have another question concerning your 9th topic, equivalence of ensembles.
Yes.
Hi, yeah, long time no see. We met each other in Janssen's birthday party.
Of course, I remember. Hi.
Hi. Concerning this topic, you mentioned that you're preparing some paper or book, or is it already written? Because it's quite important topic indeed.
Sure. So I think a good place to read about the kind of thing I do about it. First, there are 2 things to say. If you send me an email, I can probably send you the draft of this lecture, which is written out in the same beautiful handwriting that you see here, and that'll give you references. But a good place to look is, I wrote a paper called A Dozen Definetti Theorems in Search of a Theory. With Friedman, and in that paper, I survey the connection between equivalence of ensembles and Definetti's theorem, but it is a very important topic, and physicists just do it without thinking about it, and they have ideas, but there's a lot of math to do. So send me, this lecture is written out, and I'm eager to, I think there's a lot of nice stuff to do. We have been doing it, the paper is probably 30 years old, and we keep going. Lanford's Battelle note, Oscar Lanford's Finger Lecture Notes in Physics, number 20, is a beautiful development of his version of physicist theory, but he's a good mathematician, and he outlined the way that he and Ruel do that, and that opened up Baradon-style large deviations theory. That is, there's close and beautiful connections, and I agree it's an important subject. But I did write out this lecture, and if you send me a note, I'm happy to send you the lecture.
Percy, once upon a time, yeah, we all know that you wrote in your homepage that you never reply emails, but now you're requesting me to send you.
2020, it's 2020, and
I send you an email.
I'm locked up in Portugal, and you're,
okay.
Where are you? Where are you?
I'm in Graz in Austria.
Right, I remember that. And so there's nothing else to do. I'll probably stop again, but I'll answer. That's all I have.
Okay, that's great. So I will send you an email for sure. Also, I will look up the paper that you mentioned, Research of Theory.
A dozen different, that was my version of Pirandello, 6 characters in search of an author. I had a dozen Definetti's theorems in search of a theory. Let me go on, because there are more things to say, and I'm going to stop. The next topic was a topic that I like and I want to tell you about, and I call it From Algorithms to Theorems, and I'm going to stop the share. Can you see on the screen, help me, From Algorithms to Theorems? Do you see that?
Yes.
Thank you. Okay. So this is, I'm sorry, I'm just going through my lectures. This is at least a little part of, and I'll send the whole, Michael will send, I hope to be able to send the whole lecture out. This is an example of a typical lecture, but I think the topic is important and interesting. So I'm just going to give it the way I gave it, at least for 10 minutes or so. So suppose you meet a new combinatorial object, you know, parking functions or the law numbers or bell numbers. How do you begin to come to terms with this new combinatorial object? Standard moves at the beginning for everyone are questions like, how many are there? Both for small n and asymptotically. You can try to find the formula. What are natural features of the objects? You know, things like cycles for permutations or blocks for partitions. What objects have extreme features? Everybody does that. And a thing that I do is there a natural distance between the objects? Can you make a graph out of them? Is there a metric on the objects? And can I try to think about them geometrically in some sense? These are things that everybody does when they meet a new object. I want to add another basic question to this list, which is how do I make my computer work? How do I pick an object at random? How do I do uniform sampling on my set, on a computer? How do I pick one at random? And that, of course, to be followed by what does a typical object look like? And the main point of this week's lecture, pardon me, of this 10 minutes lecture, is that an explicit algorithm can often be harnessed to make proofs of theorems, thus going from algorithm to theorem. And there's a different line of work, which is very different, which is going from theorem to algorithm. And that's a nice subject too. This week, I'm going to stick with algorithms to theorems, and I'm going to, so there we are. So you already know lots of examples of that. For example, there are many ways of choosing a random permutation. The standard way, these are things I did in previous lectures, but everybody in this audience knows them, is you have n objects, 1 up to n in a list, and you pick an integer between 1 and n, say 17, and you transpose it with 1. Then you pick an integer between 2 and n, maybe 2, and you transpose it with 2. Then between 3 and n, and transpose it with 3. That's the standard good algorithm for generating a random permutation on a computer. And that writes that's a factorization of the uniform distribution into a product of, you either do a transposition or not, and you can write that down as probability, and it's very, very useful for proving things about random permutations, in particular about understanding cycles, but all kinds of things. And one example I gave of that is the following. See if you know this. If xi is 1 with probability 1 over I and 0 otherwise, those are an independent, then x1 times x2 plus x2 times x3 plus dot, 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 xn minus 1 times xn plus dot, 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 infinite sum is exactly distributed as Poisson 1. And that's surprising, and there are lots of generalizations, and that comes out of this, but lots of things come out of it. A second way of building a permutation at random is to build it in cycle notation. At stage I, you put I to the right of a randomly picked previously placed element, or with probability 1 over I, you start a new cycle, and that will build a random permutation uniformly. It puts them all on a common probability space, and that's useful in getting the distribution of the number of cycles, but also as part of the Chinese restaurant process. And that's a different algorithm, and it's very useful in certain contexts. You can place 1 up to n down in a row sequentially, put down 1 and then put down 2 either to the left or the right, and then put down 3 in one of the 3 available places, etc. That's a random permutation, and that's useful if you want to talk about inversions and other ways. Another way is we can put points down at random in the unit square, and then use the ordering of the x's, and then use the relative ordering of the y's. That's an extremely useful representation of a random permutation, and it was crucial in the Bike-Dief-Johansen theorem, but many, many other places. Many further examples coming. So that's what I mean. That is, an algorithm for picking something at random can be useful in representing it. And so, of course, one benefit of having an efficient algorithm for sampling is you can draw a random sample and make a histogram of the features you're interested in for the values of n of interest. So you can do Monte Carlo in order to check out your limit theorem or see what the answer is or see what you should be trying to prove. So I'm going to begin by treating one example, and that's all I'm going to do. I'm just going to do the beginning of this lecture in some detail. There's a non-standard sampling algorithm, which I bet you haven't seen, but it's not due to me, that really saved the day. Okay, so the topic is set partitions. That is partitions of set 1 up to n, and let Vn be the nth Bell number. That's the number of partitions of 1 up to n into disjoint blocks. Order within or between the blocks doesn't matter. So B of 3 is 5 from, everybody can be separate, or 1 and 2 can be together, or all 3 of them can be together. How many ways can you make committees out of n people? B of 4 is 15. I've always been fascinated by the fact that B of 5 is 52. What's the trick? There is a good trick. So there are the Bell numbers. And this is a huge classical subject. There's a nice chapter in Graham Knuth's Potassionic Concrete Math, Richard Stanley's Enumerative Combinatorics. There's a 700-page book by Tufik Mansour on set partitions. There's also a rich probabilistic literature around pick a set partition at random. What does it look like? And there's a wonderful article, a different article by Bert Fristed, which uses conditioned limit theorem and in much the same ways that I talked about before to say what's the size of the biggest block, how many I blocks are there, etc. I had all of the literature that I've just talked about doesn't pay attention to what's in the blocks. I have a natural family of problems that cares about the numbers in the blocks. And the problems come up in studying the representation theory of the uni-upper triangular group, so-called supercharacter theory. I won't say that right now, but suppose you have a set partition lambda, and for each block in lambda, you look at the maximum number of the block, the minimum number of the block, and then this statistic came up: the sum over blocks of the max minus the min plus 1 minus n. That's called the dimension index. And I needed to know the answer to pick a set partition at random from the uniform distribution and look at this statistic. If you Monte Carlo it, it looks Gaussian. Can you prove that? That had been an open problem for 20 years. And boy, I know a lot of ways of proving central limit theorems. None of them worked for this problem, but also the Vienna school, the people around Christian Krattenthaler had worked on this problem and couldn't do it. Let me put it that way. Calculate the mean. If you kill yourself, you could calculate the variance. And a different statistic was the number of crossings of a set partition. You can represent set partitions by a crossing diagram. So 1, 4 is this arc 1, 4. 2, 3, 5 is 2 goes to 3 goes to 4 goes, 2 goes to 4, 4 goes to, this should have 2 goes to 3, 3 goes to 5. And then you can look at the number of crossings. So pick a set partition at random. What's the distribution of the number of crossings? Again, long open, conjectured to be normal. We couldn't do it. There are other statistics. So here's an algorithm for generating a random set partition, which I find beautiful and surprising, and I'd love to know any variant of it, which anybody knows. So I'll write pi of n for the set partitions of n. So the Bell number is this number of set partitions. How do you choose lambda in pi of n uniformly? It's not even really clear how large B of n is. Of course, we know, but it's roughly n over log n factorial. There's a strange formula of Dubinsky's, which is that the nth Bell number is given by this infinite sum, 1 over e times the sum m equals 1 to infinity of m to the n over m factorial. When you think, what's e doing there? Take a look at this. It says, for example, when n is 1, it's true for all n, it says that, well, 1, the number of set partitions is 1, is 1 over e times, well, that's true, actually. And you can check it for 2, and then you can check it. Anyway, it's true. Okay, given that that's true, you can't stop me from doing this. I'm going to divide both sides of this formula by b of n. So 1 is equal to 1 over b of n times e times this. So that means m to the m over m factorial normalized is a probability distribution on n. Okay, you can't, as I said, you can't stop me from doing that. So here's Stam's algorithm, and it's easy to pick an integer from this. Choose an integer m from this funny distribution I just described. Okay, now drop n labeled balls, 1 up to n, into m boxes uniformly at random. So some of the boxes will be empty, tough, that's okay with me. Form a set partition lambda where I and j are in the same block if and only if they're in the same box. That's a randomized algorithm, which you have to think it through. It's not hard, but it's not, how hard could it be? It generates an exactly uniform random set partition. And from that representation, you can do anything you want about the kinds of statistics that I needed to get my hands on. And I'm not going to take you through that. It's written down in 2 papers I wrote with Bobby Chern and Rhodes and Daniel Kane. And you can look at the rest of the lecture. One useful thing is this gives a very good picture of what a random set partition looks like. Namely, you know what the distribution of m is. It's around n over log n. We know very carefully what it is. Drop n balls uniformly at random into n over log n boxes, and look at that set partition. That's what a typical set partition looks like. And that's easy to think about, whereas it was quite mysterious the other way. I don't want to go on, but this lecture lasted for 1 hour and 15 minutes, and I don't have any time, but I do at least want to tell you how the course ended. So let me go back to my first, try to go back to my first screen share. Lecture 11 was doing the same thing. Instead of for random permutations, you can do anything for groups, so how to understand random matrix. And so there are beautiful algorithms for generating Haar measure, from Haar measure on, say, compact groups. And this picture of from algorithms to theorem works very well. And if you haven't seen it, you might look at my article, Patterns and Eigenvalues, which I think won a prize for good exposition. Okay, so that was a little unit. The course ended with what I want to call, in case you, well, where is graph theory? Okay, here comes graph theory. I ended the course with what I call graph limit theory. And one of the things which I at least want to say, with all due respect to the wonderful, wonderful deep work that's done in GNP, it's 2020. And I don't know if you've ever looked at it, but Don Knuth 30 years ago, one of the justifications for Erdős-Rényi type graph theory was, well, there's all kinds of networks and graphs in computer science. And Don Knuth looked at 500 real graphs, all 5-letter words in English, and you connect 2 of them if they differ if they have 2 letters in common. And then for each of the 500 graphs, he computed 50 different statistics, and they look nothing like Erdős-Rényi random graphs. Everybody knows that, real graphs, real networks look nothing like Erdős-Rényi random graphs. So why are you guys all stuck on Erdős-Rényi? I mean, it's time to look at something fresh also. I mean, you're stuck on it because it's great math, and yes, of course it's great math, I agree. I built graph limit theory, talking about graph homomorphisms, convergence of a sequence of graphs, the cut distance. So I began to develop graph limit theory the way that it's done in Lovaas's book. And the probabilists did graph limit theory 30 years before Lovaas and company. And people acknowledge that now. And Svante Jansson and I wrote a paper saying, hey guys, we did a lot of that first. And of course, it's not that we did everything, but we did do a lot, and it's in the language of the Aldous-Hoover theorem. One of the things I wanted to emphasize is real graphs, real networks have weights on the vertices. How big is the company? They have weights on the edges. How much traffic goes between two vertices? And if you want to pretend you're doing anything to do with the real world, and if you're neglecting weights on the edges and vertices, you're just kidding. There is a beautiful generalization of graph limit theory to graphs with weights on the vertices and edges, and that was done originally by Aldous and Hoover. Graph limit theory 2, I gave a lecture about quasi-random graphs and used the beautiful paper by Benny and Michael on pseudo-random graphs and jumbled graphs, and then I related it. In the third lecture I gave, I gave a proof of the compactness theorem. That is, the space of graph limits is compact, and I did it without using Semeretti. You can just get it from Martingale's. I gave a lecture on permutation limit theory. There's every kind of limit theory nowadays, but you can talk about it. When does a sequence of permutations converge? When does a sequence of measures on permutations converge? There's limit objects, and that's a nice subject, and it's parallel. I couldn't help myself. I gave a lecture on V-random graph following Peter Cameron's wonderful survey. There's one random graph. Everybody knows that. Getting to the end of this, one of the themes I think is important is getting away from the uniform distribution. And on group type problems, the Plancherel measure is a useful measure on partitions, but an awful lot of work in random permutation theory now is being done in the language of Mallow's models. And I think seeing that there's beautiful probability combinatorics questions for non-uniform distributions is an important topic. And I treated the Bike-Dijk-Johansen theorem, the length of the longest increasing subsequence. Then we had 2 lectures on flag algebras and anyons. That's this beautiful subject that Rasparov and Leo Corigliano, and Leo came and gave 2 talks in my seminar, and they were beautiful talks. And if you haven't seen flag algebras, that's some effort to abstract graph limit theory to general combinatorial objects. And I gave a last lecture, and I'm going to cut because I'm over time. So that is 35 kids took the course for credit. 3 of the final projects became published papers. I hope it's a strange thing to do for me to give an overview of a course I gave to an audience of this depth and this breadth, but I hope you find it interesting. And mostly, I hope you're not too mad at me, and thank you for including me in your community. Thank you. I give up. That's the end of my talk.
So let's thank our speaker. We might have time just for a couple quick questions.
And
hi, Professor. I thank you for the lecture. Yeah, I'm really impressed by the versatile style of your lecture and your research. You can find so many deep connections with many different areas in the same line. And yeah, I think those connections may be helpful to solve some difficult open problem in some specific area, like for find the pitas for sharp p-hard problem permutation.
Come up. Just a second. You see them, I think.
It's still open. But meanwhile, we have new challenges. In recent time, there's a problem called data center scheduling problem. The problem is simple. Just give a matrix. We know according to Berkel-Van decomposition, every double stochastic matrix can be read as a convex combination of permutation matrix. In data center scheduling, they don't want the machine to run all the time. So when it added, they want to switch from one permutation matrix to another. But in algorithm point of view, how to find the minimum such kind of decomposition is still open.
Sure.
In theory, it looks like we can find a constant approximation ratio, but so far, the best algorithms can only achieve log n approximation. So yeah, it's a new challenge, but it looks like it has a lot of connection with your theory. Do you have any suggestion for the new challenge in the data set?
It seems like this question requires a long extended answer. It's not possible to answer it within 1 minute.
Wonderful to hear that there's a nice connection to the Berkhoff. I'm very interested in that. I'll try to look you up and see if you've written about it. So thank you.
Yeah.